Alright, we're up to question 6. This is a logistic function. And there was a handout on logistic and surge functions given out. But you don't need that to answer this question, but it helps to be familiar with it, I guess. Find the initial population. Well, that's the population when t is equal to 0. So we want b 0, and that's going to be 3,000 over 1 plus 5 times by e to the naught, because minus 2 times 0 is 0. E to the naught is 1, so it's going to be 3,000 over 1 plus 5, which is 3,000 over 6, which is 500 Bs. Okay, so that was part A. Now, part B, we want to show the derivative is equal to this. Now, there's a mistake here. This should have been dB dt, not dE dt. And what you have to remember, not make the mistake of differentiating this guy here. We want to differentiate this function up here and show that it's equal to this one. And to do that, we want to rewrite bt in this form so we don't end up trying to use a quotient rule. So that's what we should do. We should rewrite it in that form. Those who did use the quotient rule, it will work because the derivative of 3,000 is 0. But much easier if you rewrite it like this. And so now dB dt is 3,000, just being a constant, times by minus, that minus 1 comes down in front, 1 plus 5 times e to the minus 2t. Now this becomes to the power minus 2. Chain rule happening here. The derivative of what's inside, well, the derivative of 1 is 0. Derivative of 5 times e to the minus 2t, well that's 5 times, and what's the derivative of minus 2t is just minus 2. Times by e to the minus 2t. And working on that, we get minus 3,000 multiplied by minus 10 times e to the minus 2t. And this 1 plus 5 e to the minus 2t to the power minus 2, I'm going to put on the bottom is 1 plus 5 e to the minus 2t now squared. And simplifying the top, that becomes 30,000. Negative times a negative is a positive, so it's positive 30,000 times by e to the minus 2t over 1 plus 5 e to the minus 2t squared, which is what we're asked to show. Okay. Now, going down to this bottom question, what is the rate of increase in the bee population when there are 1,500 bees in the hive? Well, what we need to do is find out what time that occurs. When is the population equal to 1,500? And then we can substitute that value for t back into the rate equation that this one here we've just derived. So to find the time that occurs, we need to solve for when the bee population, which is 3,000 over 1 plus 5 e to the minus 2t is equal to 1,500. So that gives us 3,000 over 1,500 being equal to 1 plus 5 e to the minus 2t. Cancelling there, we get 2 is equal to 1 plus 5 times e to the minus 2t. Subtracting the 1, we're going to get 1 is equal to 5. 5 times e to the minus 2t. Dividing by 5, we're going to get e to the minus 2t is equal to 1/5. We can take the log of both sides to get minus 2t is equal to the log of 1/5. And then that gives us t is minus a half log 1/5. Now we go and substitute that into this expression for the rate. So dB dt is going to be 30,000 times e to the minus 2 times this minus a half log 1/5 all over 1 plus 5 times e to the minus 2 times by minus a half log 1/5, and that's all squared. Now this simplifies quite nicely. Minus 2 times minus a half is 1. So it's 30,000 times e to the log 1/5 all over, same thing happens down here, 1 plus 5 e to the log 1/5 squared. Now the log of e to the log of 1/5 is just 1/5. So that's 30,000 times by 1/5 over 1 plus 5 times by 1/5 squared, and that becomes 30,000 divided by 5 is 6,000, and this becomes 1 plus 1 squared, that's 2 squared is 4, so it's 1,500 bees per month. Okay, got a bit squashed in there, should have made more room over here. But let's write it down here. So the rate is equal to 1,500 bees per month. Okay, and that's question 6.